Today we have a packed agenda. We have three main topics, hopefully of your interest. The topic that we're going to discuss, as Christina said, is real-time data for water loss control. So we're going to break this down into these three pieces. The first one is we're going to talk about the data challenge in general. We'll get into that in just a second. Then we're going to go into the second part of the topic, which is around DMAs and VDMAs, virtual DMAs in particular. And then we're going to look at the practical side of the story with some case studies. So with this, and to start, as we said, the main topic of today is real-time data for water loss management. So when we dive into the first part of the topic, the data side of the story, I'd like to talk about first about the data challenge. And when I talk about the data challenge, I'm not really referring to the amount of data that is already out there. I think you will agree with me that over the past few decades, water and wastewater utilities have invested in a lot of data-driven technologies. We're talking about SCADA, AMI, CMMS, GIS, and so on. So again, the lack of data is not a big issue. In fact, I would even argue that that has put the concept of digital journey and digital transformation on the map, and some utilities are already embarking into these initiatives. And also it's driven us to the point where in the market today, conversations around machine learning, artificial intelligence, data models, digital twins, they're embedded within all the conversations that we have in our water and wastewater industry. So if the amount of data is not the problem, is not the challenge, what's the challenge? And I think the challenge is, the big elephant in the room is where is that data and how is it being used? Right? So we know that in order to use these data-driven technologies, we need a solid foundation. But at the same time, we know that all these investments that I just mentioned at the beginning on SCADA, AMI, and so on, they've been normally done in silos. They've been done because a utility department had a specific issue, and they went and they acquired certain technology, a software or digital equipment. But when selecting those solutions, back then, the concept of integrating that data with other parts of the organization and sharing the data from that solution throughout the whole company, but probably not at the forefront of the criteria that was used to select that technology. So that puts the conversation on what is that data, and also how it is being used. How are we turning that data into really information, into something that operators and managers need in their day-to-day, getting that information the way they need it, with the quality they need it, when they need it, and trying to avoid searching for all that throughout the whole organization. So again, with all these investments being done in silos, one of the things that has happened, at least in my experience, what I've seen over the past several years, is that integration efforts have already started to happen. Some utilities obviously have realized that bringing data from operations to engineering or from customer management to operations is really valuable. So they embarked into some integration efforts. But in a lot of cases, those integrations have been done in pairs. When I say in pairs, it's like integrating the SCADA system with the hydraulic model, or the AMI system with your customer information system. So again, they've been done in pairs, and throughout the years that has been going on, and has led us to a point where today we see a type of architecture that I think is very pervasive in our industry, and some of you will recognize, which is the spaghetti architecture. The spaghetti architecture is no other than integrating those systems one-to-one or one-to-two, as I said, like SCADA model, AMI, customer information, but not looking at this holistically. So what this means is, this is something very difficult to maintain over time. And we're seeing that today in conversations with utilities. That's something that comes up all the time. I mean, if we look at simple examples on, for example, think about an asset, think about a valve or a pump. That valve or that pump is named a certain way in your SCADA system, is named something different in your CMMS, is named differently in your GIS. So when you need to put all those three systems together for that asset, it becomes very cumbersome. It becomes very, very difficult to do. If you expand that example to all the assets and all the processes within the utility, I think it's very obvious that this is very difficult and very costly to maintain over time. At the same time, it also promotes the same data silos that we're trying to break here, because all the relevant data stays in the source systems and it's not put in front of everybody else within the organization. And as I said, like, it is very ineffective in the midterm because of the cost, but also we all know that more and more digital solutions are coming in and more data are getting into the water and wastewater utilities. So that plate that you see there is going to keep growing and it's going to be even more complicated to maintain. So this is part of the challenge. This is 50% of the challenge, because the other side, this is on the background, but at the forefront, we're taking all this complexity and we're putting this in front of the users of that data. So what this means is we're forcing our users to go to different systems to solve one specific problem. And different systems with different logins, different user experiences, they also find data. They don't find information. They might find a pressure value, but not what that pressure value means for them in their day-to-day. So what that means is there is a lot of manual work just to extract all that data from all these different sources, putting them all together. I've seen more Excel sheets that I can count over the years. So it becomes very cumbersome and very time-consuming for the users of that information, and that time could be better used to solve the problems. In this case, when we're talking about water loss, than really going out there and trying to fetch that information. So this has been going on for a while. I think we all know about this, but at the same time, this is something that some companies and some utilities have started to try to solve. And there's some at the forefront of all this. And one of them is Global Omnium, which spotted these issues several years ago, and they took the necessary steps to start breaking down these silos and started solving this problem. So Pablo is going to walk through this for us. So Pablo, this is for you.
Thank you, Manuel. Very good to hear. That story actually is very, very similar to the story that we lived many years ago, Global Omnium. And when we introduced ourselves as a company at Idrica and our platform, Goagua, we like to tell the story of how this was born from an actual utility. So that's why we typically like to show this page. So Global Omnium is a water utility that provides water and sanitation to over 7 million citizens in Spain mostly. With the largest city managed, the city of Valencia, which is the third largest city in the country with over 1.5 million people. From Global Omnium many years ago, in the early 2000s, we started to find these issues that Manuel was just talking about, right? Issues related with how are we going to use all that data that is coming from all these systems that we are investing in. They're not cheap systems. They're systems that are very valuable, but at the end, they're generating a huge amount of data that our operators or engineers are not able to process because they're humans, right? It's billions of data points every single year that nobody can actually process manually. That together with also some human and cultural issues that we were having, there was a wave of retirement. We needed to keep that knowledge inside of the company, that generational gap. That made us start a big transformation within the utility to actually start building a data-centric platform so that every single technology, every single data-generating silo, we could be bringing it to a single place, and then from that, make it available to everyone who would need to know the exact flow, the exact pressure, the exact production of water for one exact point in time, right? So that was how we started in the early 2000s. We took a little bit of time. Obviously, we made mistakes. We learned from them. But the result was that in 2015, approximately, we created a platform that we named Goagua that is providing not only Global Omnium with this solution to have data-centric in all of the utility and a series of solutions, but that we started bringing it to other utilities globally. And we started bringing it to other utilities, first in Europe, then in the Americas, and then worldwide. Next.
Perfect. So in beginning of 2023, Idrica and Xylem joined forces, and with the Guayua platform that Pablo just talked about, together with the technology and applications we had at Xylem, we created Xylem View powered by Guayua, which is a water-focused software analytics platform for the full water cycle. And in essence, what it does is trying to solve the problem that we were just talking about a moment ago. Connecting and organizing all these data silos, all these investments that the utilities had already made, and take all that data and organize it so it can be used across the whole organization, either directly as raw data, but also through applications that are already productized and pre-canned, like we're going to talk about later, leak detection. So the operators, managers, engineers can access that information, not the data, but the information when they need it and the way they need it. As Pablo said, this is implemented all over the world in over 400 utilities. And very importantly, also as we just heard, this is, again, water focused. So it comes with that background on operations and the information coming from a water utility. So we say that it's built by utilities. That's how it started, as we just heard. And it's built for utilities with that water and wastewater mentality in mind.
The way that we build this, as I was mentioning before, was thinking from the utility perspective, and I'll go from the bottom to the top. As a utility, we had many different sources of information. We had invested in over 1 million AMI, over 1 million smart meters from different technologies, including sensors. We had invested in thousands of sensors. We'll talk later about district metering areas or DMAs. But in order to have these over 3,000 DMAs in the city operative, we needed sensors to measure flows, to measure pressure. We also have sensors measuring levels, water quality. We had many different SCADA technologies, not only from one brand. We had distributed databases, enterprise resource systems, GIS, CMMS. And we didn't want these systems to disappear. We wanted anyone who was using the systems to continue using them, but we wanted to have a layer that brought all of that together, that linked every single asset to its data, and that would make it available historically and in real time to anyone who would access that, regardless of whether that data point is coming from a Siemens SCADA or a Census meter or another brand, right? So we did that. That's what we call a single data model, or the unified smart water engine, where we bring all that information together. And then as a utility, we also realized that the operators, all the people in the field and basically doing the work out there, they needed to use the data for different use cases, right? So that's when we started, after doing that work, putting together a series of use cases, packaging analytics, making basically data scientists and developers work together with operators to solve the key problems that they had. Today we're going to speak about one specific problem, which is the non-revenue water or water loss control issue. But the way that this was developed was to solve all of the different problems that utilities typically face, from non-revenue water, water production efficiencies, real-time modeling, pressure control and management, energy savings, and also on wastewater, right? So that's that layer that we call modular data applications and operational intelligence, which provide utilities with this capability of using that data and not reinventing the wheel from the very beginning on how to use it. Next. Right, so now we're going to talk about how we leverage district metering areas for water loss control, and Manuel is going to give you a little overview of how to do that. Perfect. Sorry, it was my turn. So how we talk about non-revenue water and water loss control. This matrix, I'm sure many of you have seen it already. It's the IWA or AWWA water loss control matrix. And when we talk about non-revenue water, which is basically the water that we are losing from the moment that we produce it to the moment that we sell it or serve it to our clients, right? Normally, the biggest component, if we go to the next page, is what we call real losses, right? Unless your utility has a very old or inexistent metering system, which is not likely, right? We're going to find that the biggest component of non-revenue water is going to be real losses, right? Which real losses actually account for everything that you're losing in your water distribution system and you're not accounting for. So today we're going to focus on that and talk about different strategies to reduce that, including the creation of district metering areas to actually identify and quantify in what areas of the city you actually have more real losses. But we also are going to talk about other things that complement this, right? Like the existence of advanced metering infrastructure or advanced or smart metering is also going to help you identify and quantify non-revenue water in real time, right? That's something that utilities don't typically use for that, but it's going to be a great complement to your monitoring and control of the DMAs. Acoustic monitoring is also something that if you want to start locating and pinpointing those leaks quickly, you should use as a strategy complementing this DMA strategy. And obviously, analytics and speed of repair, right? If you want to reduce non-revenue water, the moment that you detect you have an event, you have an issue in your network, you have to make sure that someone is out there finding the leak and fixing it as quick as possible. Next.
Perfect. Thank you, Pablo. So some of you, maybe most of you, are familiar with the concept of district meter areas or DMAs, released, with the concept of traditional DMAs. We're talking, of course, about hydraulically isolated areas or sectors. So in essence, what we're doing is, of course, taking the distribution network and breaking it down into different pieces, just to put a word to it. And then we measure the inflow and whenever possible the outflow of that area, is to get a water balance in place and apply certain analytics around minimum night flows and so on, just to understand what is the situation of that DMA and spot any water loss problems within those sectors. This is useful, of course, because now we can start pinpointing much more clearly which areas of that network are problematic, and we can go down to that. So again, traditional DMAs have been around for many years, and again, they're a very good tool. On the other side, though, they are very heavy on the type of equipment that is required. Normally, fixed equipment in the field requires also a lot of resources to go and manage that equipment, those valves to isolate the area, and also the investment that needs to be done to go in the ground just to install all that equipment. So again, very good tool, but it has a certain high cost in terms of not only implementing it and maintaining it, but also running this efficiently. Now, we're talking about real-time data. We're talking about the amount of data that is out there. So a complementary approach to traditional DMAs is a concept of virtual DMAs. So virtual DMAs, in essence, is the same thing. We're taking the full network, we're breaking it down into different areas. But in this case, as Pablo was saying, we're going down the path of using the data that exists out there. On one end, we'll have AMI data, so that provides us the consumption side. And then we can use flow meters to isolate certain areas and create those virtual DMAs. And the benefit of that is that those flow meters, normally insertion flow meters, they're less costly and they're they're easier to implement and maintain than the meters that are used for traditional DMAs. So again, a more flexible approach to creating those zones and those areas, but also getting the value of being able to apply the same analytics behind these virtual DMAs. Now, what does this give us? Well, if we have a full network, of course, the first thing to do is to run a full network analysis, look at water balance, what Pablo was showing before. And in this case, let's imagine we have our network, we have a non-revenue water of 30% for the full network, which is great as a first idea, what's happening. But then it doesn't give us information on what to do. Where do we go to start looking for those problems? Where do we go in the network to start looking for leaks? Right? And that's when the concept of sectorizing the network, creating those DMAs, come into play. Because by doing that, we break the network down into different areas, and now we can start applying the analytics to each one of these areas and start categorizing them. In the simple example that we have on the screen, we have 3 DMAs, and we see that in this case, the DMA3, virtual DMA3, is the one that has the highest problem. Therefore, we can now take our resources and start moving them to look for the problems in that area, because very likely the return on investing those resources in that area is going to be higher than if we go to the VDMA1 or VDMA2. So again, it's a way of starting to get a little bit more granular on how we attack the water loss problem. Now, how does this work? How do we make this happen? So in this case, what we said before, we have our master flow meters, which gives us the production getting into the network. We have our customer meters, ideally AMI, because that will give us much more granularity and real-time data on consumption. So we can start thinking about water balances in a much more real-time scenario. And then the third point, when we go to the virtual DMA approach, is installing those flow meters, the VDMA boundaries. So those boundaries, normally when we work with our clients, we sit down with them first, we look at the network, we figure out where those boundaries are going to be, and then we go with those insertion meters, which, as I said before, they're less costly and they're easier to implement than the fixed permanent meters and all the valves and so on. So we create those virtual DMAs, and from that point on, we start getting the data from the field. We have then the analytics behind all that. So the software helps us start ranking those DMAs with the highest problem, with highest loss and other categories. And from that point, now we can start digging even deeper. As Pablo said at the beginning, this is the first step. Then we go and we're going to start saying, well, if VDMA3 is the one that is the most problematic, let's start going down, and now we can start implementing other technologies like acoustic sensors, which of course that data can go back to the software to refine the analysis. And then from that point on, we can send a crews out to that area and start sweeping the network and confirm the precise location. That data will also go back into the software for additional analytics. And from that point on, now that we know what the problem is, we'll send out the crews to go and look for the problem. So this is, in essence, and high level, how the process will look like. And you might say, Manuel, this is great, but it's still very, very theoretical. Where has this been done before? So this is a perfect time to move on into the real cases. And Pablo is going to walk us through some success stories where he's going to show how some utilities have started to implement this approach into their operations. So Pablo, pass it on to you.
Great, thank you. We're going to talk about 3 client studies that we have been working on for a while at different levels of maturity. We'll start with a city in the south of the US that we started working together a few years ago. And they started with, they came to us saying, look, we have a high non-revenue water, we have water loss, we know that, but we don't know where to start looking. And we need your help to actually prioritize where to start looking, because we don't really have the resources to start looking everywhere in the network, right? We're still working with this client, but this is a great story about how the digital tools that Xylem and Idrica provided to them are actually helping them bring together AMI data, flow data, pressure data, water production, SCADA data together to start prioritizing actions and gain ROI of their actions. Right? Next page. In this city, we started with 14 district metering areas. We left the city center out for the beginning. Now we are already integrating that. But what was important for them was that from being totally blind, from having just total water production at the SCADA, and then being able to see total water usage at the end of the month from their bills, they went to a system, which is what we provided them with, in which they could see pretty much in real time for every single district. A district is composed by, it's an area where you have a series of meters. It could be from 100 to 100 meters to thousands of them, right? And depending on how they are configured. So for each of these systems, for each of these districts, the city started being able to see exactly where they had issues. The ones that you see that are more green are because they didn't have any significant issues in terms of non-revenue water. They had a pretty low estimates of non-revenue water, and they didn't have any pressure imbalances. And the ones that you see in red is because they had some events. They had some peak, some overnight increase of flow, and they could have any type of leak, any type of problem within them, right? So this is how we started looking at this and prioritizing actions. Next page. What the system is also helping them do, and this is very interesting, is for every single one of these districts or areas, the city can actually compare in real time how much water is being supplied to the actual district. So for example, in this chart at the bottom of the page, you can see a blue line in the background. That blue line is the inflow to the district meter area at an hourly basis, where you can see a pattern of less consumption at night and more consumption during the day. It is overlaid with a green line. This green line is actually the aggregated AMI, aggregated consumption from all clients. Luckily for us and for them, they did have 100% of AMI deployment in the entire city. So because of that, we were able to bring all the data from their census AMI system and overlay it in real time with their insertion meters in real time so that they could compare one with the other. And that is very valuable to them because it allows them to see, to detect whenever they have any problems. If there was a leak, a pipe burst in the system, the blue line very immediately goes up and starts giving an alert, telling them, hey, you probably have non-revenue water here. That's a little bit of the analytics and the solution what can give them to them. Next page. We are also helping them a lot by visualizing this water consumption at the client level. So before this, they were only using AMI data to bill customers at the end of the month, right? With this, they're starting giving it a lot more use to the AMI data, to the water consumption and water usage. Why? Because they could see, for example, on the left, you can see that there's a map where they can select any time range and they can start seeing what pockets of consumption they have in the city. They can compare that in the winter, in the summer, and that gives them a lot of know-how of where their biggest consumption within the city is. But then the use of analytics and the use of data science is also helping them identify events. For example, on the right-hand side, you see that there's a client, an example of a client that did have an anomalous consumption for a series of days. And this was flagged very quickly as an anomalous consumption, and it was an actual burst within the client's household. That was alerted very quickly, and the client could stop this from happening in a matter of 1 or 2 days. That couldn't have happened if we didn't have AMI and we were not looking at this continuously. Next page. And ultimately, another thing that the utility is using very efficiently, and it's very helpful for them, is, okay, you're giving me an alert system. We're able to see, to drill down to the meter level. We'll be able to see the DMA level, what's going on. But then at the end of the year, or at the end of the month, they need to submit a series of reports of non-revenue water, calculating the different components of that matrix that we were seeing at the beginning of the presentation. Well, we're also helping them with that because they have the information from their SCADA on production. They have the information from the demand on the AMI system. Putting all that together with the GIS information, the pressure information, allows them to have these matrices calculated automatically, right? So that gives them a lot of a lot of tranquility at having this data at their fingerprint for whatever time range they want. There's also one more thing in the next page. You can see that this utility, for example, they actually do have some flashing events that they upload manually normally to the system. Well, we also allow them to do that here with Excel templates so that they can be entered into the AWWA water loss reports. The second example that we're going to talk about is the city of Chino in California. This is a city that actually didn't implement DMAs, but we still are using the data analytics on the platform to help them basically quantify how much non-driven water they have and do some analytics around water production so that they can basically understand what is the quantification of their problem at a high level. Obviously, as soon as they decide to implement DMAs, they could do that, and they could include that here. This system, this city, what we did for them is we integrated all of their SCADA information in real time, all of the distributed sensors, flow, pressure that they have between pressure districts instead of DMAs that have 3 big pressure districts. All of the AMI, they have different systems for AMI, so we also integrated that in real time, their work order system, their GIS, and their hydraulic model. So we used all that integrated to provide them with a lot of insights about how much water production they were having, how much non-driven water they were having in real time, how much issues they were having by pressure district. And this started giving them some insights about their water distribution system. Next. One of the things that we did with them, for example, was about water production, right? Because especially in California, you have different water productions and you have to control your water rights because you have sometimes you have to import water from other water agencies. Sometimes you produce your own water. So they needed to have a very clear and very close control of water production by system. They needed to look at what wells were producing how much water, but as well how much water was being produced by treatment plant. And this was coming from different SCADAs, and these SCADAs were only saving 1 month of data. So we basically connected all of that together into this dashboard so that they could actually control and see how much water they were producing, and they could go back in time and see trends for unlimited amount of time. Next. We also helped them do some economic analysis. So obviously, because what I was saying before, sometimes you have to import water from third-party agencies. Sometimes you have to produce it yourself. So having this connection with your economic or financial systems, with your ERPs, and quantifying your water production and how much you're spending per gallon of water per source, and quantifying at the end of the day, well, I spent $50,000 producing water today. And these mostly came from third-party agencies or from my own well production. And this was higher than yesterday because of that. That was something that they were not doing before. They were just doing that, an estimation at the end of the year. But having this at their fingerprint every single day, that was very, very valuable for them because they could start doing strategies to actually steer their water production strategies and be more economically effective. Next. And obviously, what I was showing you before from the other city in the south of the United States, they also had a very granular view of their AMI data, of their water consumption. In this case, even if they had 2 different AMI systems, that was okay. We integrated all the information and were able to give them not only aggregated water consumption levels over the whole city surface or area, but also individually by meter so that they could detect alarms and events whenever a client had a burst, a leak, or any other issue. Next. And the very last example, which is a pretty advanced example, and that's the city of Valencia, which is one of the cities that the Global Omnium group actually manages as a utility. And I talk about this example as a very advanced, just because this is where the platform was born and has basically been doing that for over a decade, is the city of Valencia. With the platform, with the Xylem powered by Guagua platform, this city, which has over 1.5 million people between the main city and the metropolitan area, is integrating pretty much everything from the water treatment plants to the water distribution network and the sensors, GIS, hydraulic models, work order systems, the financial systems. And this is helping them not only integrate all of their distributor areas, they have over 2,000 of them to reduce non-revenue water, but they're also integrating their hydraulic model with the real-time data to make decisions, forecasts, and see how the network is going to behave in real time under whatever scenario. Next page. As I was saying before, this city was the first European city with the first full AMI deployment with almost 1 million smart meters, including different platforms. Obviously, having different technologies for AMI initially was a challenge, and this is why the platform was created, to start integrating different technologies of different brands. But that also helped us integrate not only AMI, but also SCADA, GIS, field operations, and the ERP. First, this platform started integrating all of the AMI analytics for revenue management and customer service. So having all of the analytics around AMI helped the city start being proactive in the way that they communicated with the customers and reducing a lot customer insatisfaction, right? At the beginning, they had a lot of calls regarding consumption and disagreements, but their customer calls went down by 60 to 70% after they started being proactive in the way that they manage them. Second, proactive non-revenue water reduction program. This was a big problem in the city. There was a big problem because they were starting with levels of non-revenue water that were between 20 to 30%, and that was a lot of water loss throughout the network. With this program and the digital tools and analytics, they got to reduce by 65% all of the water losses they had throughout the network, becoming one of the most efficient cities in the country. That was a major item because it allowed them not only to save money in water treatment and energy, but also to make sure that they didn't have to invest in more water sources like desalination plants, like wells, etc. And finally, the digital twin. The digital twin is a concept that you've probably heard a lot, but this is something that started a while back for the city. Once they had all of the data integrated in one place, they also started integrating their hydraulic models and a bunch of different algorithms so that they could actually see what's going on everywhere in the system, kind of like a Google Maps for water, where they could see anything that's going on in any single pipe, in every single node, and simulate any different scenario and behavior. Next. So this cycle is showing a little bit of how the city manages non-revenue water. And this is a series of processes, but tries to explain how the full circle happens, right? From having real-time data from different AMI sensors, measuring flow, measuring pressures, right? From that data is actually coming to the system where you can see non-revenue water in real time and have alerts telling you whenever you have an imbalance. From that, the system is actually connecting to the hydraulic model to see what is the most likely area where you could have a leak within the DMA. From that, the operators can actually see mixing that information with how pipes have been, like the age of the pipes, historical pipe bursts within the area. They can know very well where these heat maps of likely leaks could happen. From that, the operators are communicated. The work order system actually receives the notification automatically, and the people that are in the field go look for that leak. In the next page, they have tools, 3D tools that they can use to actually access the assets in the field. And then finally, once the asset is repaired, that comes back into the system and is reported back, so that this full circle happens, and it happens as fast as possible, which is the objective of making this happening, right? Reducing non-revenue water is about detecting events and making it as fast as possible so that you can close the cycle in 1 day, 2 days maximum. Next page. And this is a view of the digital twin that I was talking about before. It's very interesting because This is a map of the city. You can see the left corner and at the top corner the two plants providing water to the city, and then you can see the entire center of the city. Obviously, we don't have sensors in every single pipe, in every single node. But the system, what it's doing, it's using all the SCADA data that is coming in real time, and it's using about a network of 150 to 200 pressure and flow sensors throughout the city. And with that, it's just applying analytics and the hydraulics that we have from the entire city to return to us every 30 seconds to 60 seconds a real-time view of what is happening in the entire city. And that's very interesting because I do the analogy many times of Google Maps. If you today go into your Google Maps application and say, I want to go to the airport, you can see right now how much time you're going to take there and where you're going to have traffic jams. That doesn't happen in water networks because they're underground and they don't have sensors in every single point. So this is a little bit what this is doing for the water network. It's allowing the operators to see where you're having issues, where you have pressure problems, where you have low, high pressure in real time, and it's allowing them to simulate any scenario, pipe bursts, hydrant flashes, etc. And this is it for today. Thank you so much. I think we're going to open for questions now.